All right. Well, hi, everyone, and thanks for attending today's CGD seminar. Before we get started, I'll remind everyone of our CGD Code of Conduct here, where we share the air, acknowledge teamwork, encourage innovation, show appreciation, consider new ideas, and offer constructive feedback. I'll also ask that everyone please keep themselves muted and hold any questions until the end. If you have any burning clarification questions, you can please put them in the chat. Now it is my pleasure to introduce today's speaker. Yaga Richter is a scientist 3 in the climate change research section here in CGD. She received a BS in mathematics from SUNY Purchase and a PhD from atmospheric sciences from the University of Washington before joining NCAR as an ASP postdoc, where she has been ever since. Her expertise and interests include gravity waves, middle atmospheric dynamics, quasi-biennial oscillation, subseasonal to seasonal forecasting, and geoengineering. And she is co-chair of the CESM Earth System Prediction Working Group. Her talk title today is Impacts of Varying Climate Intervention Strategies Utilizing Stratospheric Aerosols on Stratospheric and Tropospheric Climate. So Yaga, go ahead and share your screen and take it away.
Thank you for the introduction, Dan, and thank you to all of you for tuning in. Today I'm going to talk to you about climate intervention, which is a topic that elicits strong views and emotions, and that kind of makes it a difficult area to work on. So before I go in any further, I'd like to express my appreciation to all of the collaborators listed here who've contributed to the research that will be presented. Their collegiality and responsiveness have really allowed not only for substantial progress to be made, but have also made work on this topic a lot easier. A special shout out to the Cornell team, who has been a true partner in this work, and a lot of what you see here could not have been done without their contributions. So let me just begin by describing briefly to you what led me to this work. I have spent majority of my career at NCAR in the stratosphere. So it's this layer here above the troposphere, and is characterized by two dominant features, the Brewer-Dobson circulation, which goes up in the tropics and comes down over the poles, and then the quasi-biennial oscillation of the zonal mean wind, which is about a 28-month oscillation and which remains in the tropics. And the Qbo is driven largely by gravity waves, which in most climate models are parameterized. So in one of my earlier days as an ASP postdoc, I completely overhauled this parametrization. And to this day, it plays an integral part of WACCM, and I'll come back to that, why that's important. And largely it is important because now WACCM has an internally generated Qbo, which has not been, which is relatively a new feature to the model. So WACCM is the whole atmosphere community climate model, and I'm only showing you here the troposphere and the stratosphere, but WACCM extends all the way to 140 kilometers, so it includes the mesosphere and the lower thermosphere. And because of all the complexity that's in the upper atmosphere in this model, that we can use this model for climate intervention research. And interactive stratospheric chemistry is also really needed. So that's one of the unique things about WACCM. So in recent years, I spent a lot of time on developing a subseasonal prediction system, both with CSM2 and in CSM2 WACCM. And I'll come back to that, how that's not important for our current research on climate intervention, but I think that's where the future lies. All right, so just so we're on the same page, climate intervention, what is it? It's a deliberate large-scale manipulation of the planetary environment to counteract anthropogenic climate change. So it's a very important topic to society, and I think it's also an opportunity for NCAR to play a larger role in this field. So in particular, the NCAR 2020-24 strategic plan calls for research to advance development analysis of climate change mitigation, intervention, and adaptation strategies. It calls for contributing relevant information to policy and decision makers on possible pathways to limit global warming to 1.5 C or 2 C above pre-industrial temperatures, and to build strategic partnerships aligned with science and technology goals, particularly focusing on collaborative approaches to scientific and societal challenges of mutual interest. So today I'm going to walk through climate intervention research at NCAR with the community, starting about 2015 with a present on recent work And I'll discuss a multi-institutional partnership with the academic, commercial, and NGO partners, which have really enabled quick progress in this field. And then lastly, I'll focus on future directions. All right, so the Intergovernmental Panel on Climate Change 2021 put out this report, which shows the global surface temperature change relative to pre-industrial period. And all these different color lines here are different SSPs or shared socioeconomic pathways. And each one of these pathways makes assumptions about emissions. The two blue ones are the most optimistic ones, for example, SSP 1.19, which assumes net zero CO2 emissions around 2050. And it's the only scenario that would keep to the Paris Agreement or keep the temperature below 1.5 C. Most likely, and right now, we are headed for one of these other futures. So the moderate scenario, it's SSP 245, and a really high emission scenario, SSP 585. So depending on which scenario you use and which model you look at, the global mean surface temperature will reach 1.5 degrees over pre-industrial somewhere between 2025 and 2035, and over 2 degrees in 2035 to 2060. So that's not really that far away. And Arctic will become ice-free towards the end of the century. Again, the date depending on the scenario and the model that you use to make that projection. The number of people affected by climate change is the entire world's population, or about 8 billion people. However, the changes are not equal across the globe. So as you see in this top panel is the simulated change at 1.5 C, 2 degrees, and 4-degree warming. And there's a few features you see that the northern latitudes in the northern hemisphere are warming a lot more than the tropical regions, and also that the northern hemisphere warms more than the southern hemisphere. The bottom panels show you the associated precipitation changes, and most of those over land happen in the tropics, and they typically happen, well, most of them happen in areas of developing countries where there's very few resources for climate adaptation and mitigation strategies. And some of these changes you see are up to 40% change in precipitation. So the mean changes are also associated with changes in heat waves, heavy precipitation events, and drought. So the time is ticking and we really need solutions. So reduction of emissions needs to be the top priority. There is absolutely no debate that. However, climate intervention could be a part of a strategy to reduce the worst consequences of climate change. And again, I stress it's not a substitute for decreasing emissions, but perhaps the technology could be used for a decade or a couple of the decades to keep the global mean temperatures to what we believe are livable levels. So this diagram here summarizes solar climate intervention methods. Today, I'm going to focus primarily on SAI, or stratospheric aerosol injection. So by increasing the amount of stratospheric aerosols, we reflect some of the sunlight back to space, therefore cooling the Earth. There are others studying marine cloud brightening, for example, Jack Chen at NCAR, but I'm not going to cover that today. There's also other climate intervention methods, CO2 capture, carbon dioxide removal, ocean iron fertilization. Again, I'll mostly focus on SAI today. And why do we think SAI has potential to work? It's because its natural analog are volcanoes. In every large volcanic eruption, in observations has shown a decrease in surface temperature. So volcanic ash is largely composed of SO2, of sulfur dioxide, and that's what we will be putting into our model to simulate climate intervention using stratospheric aerosols. So going to volcanoes, I'm going to show you a movie of a few volcanic eruptions, and these are simulations by Mike Mills. And what you see here, what is in the contour is the volcanic aerosol column burden, so basically where the aerosols are forming. And we're seeing this movie on the left, that these volcanoes are going off in the northern hemisphere, and you see that the aerosols are mostly covering the northern hemisphere. And if you get an injection south of the equator, first you see that the aerosols spread really quickly with longitude, and then they begin to fill the hemisphere of the injection. So just keep that important point in mind. as I will show you the eruption of Mount Pinatubo, which happened in June 1991. And you see slightly something different here. So yes, first the aerosols filled the tropical belt really quickly. But also just a few months after the eruption, you see that almost the entire Earth is covered by aerosols. And the difference between what I showed you on the left and on the right is the location of the injection. So Pinatubo happened really close to the equator, and that allows for different propagation of the aerosols and different transport. And I'll come back to that in a few minutes. So the early studies of stratospheric aerosol injection or climate intervention did things that were simple. For example, they did in the sun, prescribed aerosols, maybe injected SO2 somewhere, and then examined the impacts. And all of these studies demonstrated the ability to counteract the increase in global mean temperatures. However, there were lots of unintended side effects and risks. So for example, a lot of these studies found that it would be overcooling in the tropics and in warmer temperatures in high latitudes, which would lead to reduced rainfall, shifts in rainfall patterns. And because of this warming in the polar latitudes, the Arctic sea ice would still be melting. So what I'm going to talk to you today, and this is methodology we've been pioneering with Ben Kravitz from Indiana University and Doug McMartin, is a little different approach. First, we pick the goals, what we would want climate intervention to do, and then we pick the SO2 injections to meet those goals. And our goals are right now all related to surface temperature. So you saw before, this is the change in temperature that we're trying to offset. So firstly, we would want to keep the global temperature at our target level. We want to keep the equator to pole temperature gradient, or T1, at the same level, and also the pole to pole gradient, T2. So in the next few minutes, I'm going to describe to you single point injections experiments that explore the sensitivity of the system. And then I'm going to move on to large ensembles of 21st century simulations with CSM1 and CSM2. So CSM1, WACM, I mentioned, is already Community Earth System Model version 1 with the whole atmospheric community climate model as its atmospheric component. It's got a couple land, ocean, sea ice, atmospheric chemistry with prognostic aerosols. And this is a 1 by 1 degree model, and it has an interactive Qbo. And WACM has all the same tropospheric physics as our low top model default CSM1. To CSM2, there are quite a few differences. So instead of just middle atmosphere chemistry that we had in CSM1, we're running now with fully troposphere, stratosphere, mesosphere, and lower thermosphere, or TSMLT chemistry. There's a 4-mode aerosol model, MAM4, instead of AM3. And there's been lots of changes in the troposphere, including the addition of club macrophysics and unified turbulence scheme, new form drag parametrization. So these CSM1 and CSM2 are actually quite different. All right, so here's our back to the cartoon of the stratosphere. And we'll start with single injections of SO2 with a constant annual injection rate of 12 teragrams SO2 every single year. And to put this in a framework of what has happened in the historical record, observationally, we believe that Mount Pinatubo emitted about 20 teragrams of SO2, but those are estimates. So it could have been around 10 or 15. But so what we're putting in is roughly 1 or 1/2 Mount Pinatubo in our simulations, but every single year. So that's a lot of volcanic ash. And when we did our first studies with CSM1, we did injections where we have these yellow dots, so 5 kilometers above the tropopause, and these green dots 1 kilometer above the tropopause. I'm not going to show you the results from these green dots because they turned out to be less efficient. Because if you look at this cartoon of the Broad-Dobson circulation, you see if you inject things low that they're going to clearly fall out pretty fast. Whereas if you inject to the higher branch of the circulation, the aerosols remain in the atmosphere for somewhere about 2 to 5 years, and it will depend on the location, altitude. With CSM2, we've gone to injection at a constant altitude. And this is because in CSM2, we're trying to do things a little bit more realistically, thinking of possible implementation scenarios And 22 kilometer is really the highest altitude that available aircraft could reach if they were carrying SO2. And really that altitude is not really dependent with latitude. So we just picking this fixed altitude of 22 kilometers, which is really a grid box centered on exactly 21.7 kilometers with a vertical extent of about 1.3 kilometers. All right, so what happens when you inject in these individual locations? And you see very much something similar to what I've shown you in the volcanic movies. So when you inject at the equator, you get this pileup of aerosols in the tropics, but a little bit goes both to the south and the northern hemisphere. And as you move your injection points away from the equator, you see that the aerosols start spreading a little bit more into the extratropics, but there's also there's always a little bit left in the tropics too, unless you go to 50 south, at which point you're injecting fairly low and your aerosols start falling out fast, and therefore they're not really staying long enough to produce as much impact as they could. So for all the future simulations, we decided mostly to use injections at 15 south, 15 north, 30 south, 30 north, as if you combine them together, they can provide pretty even coverage from pole to pole. And I'll keep showing you some simulations with the equator. However, we've shown that the side effects with using the equatorial injections are much larger. All right, so what happens when you inject these rather large amounts of aerosols into the stratosphere? Well, firstly, the stratosphere heats. And in these green lines here, you see where the aerosols are going. And for 12 teragrams of equatorial injection, 25 kilometers, our model predicts a heating of 7 Kelvin, which is quite a lot. And then for that, you get about 1 degree of cooling throughout the troposphere. So once you heat the stratosphere, you're also going to change the chemistry. For example, ozone. So you see here that the ozone concentrations decrease in the area that there is most heating, and then there is also changes in water vapor. And ozone increases above that, mainly to the reduction of NOx. Because you've changed the temperature, you're going to change the entire circulation of the stratosphere. So following the thermal wind equation, the zonal mean wind also changes. So for example, you see the intensification of the polar vortex and also significant changes in the equatorial region. And W bar star is a measure of the residual circulation, so the Brewer-Dobson circulation. So you see that you get increased upward motion in the tropics and decrease over the poles, so you basically sped up the Brewer-Dobson circulation. All right, what does it look like for injections away from the equator? Well, here's the temperature and zonal mean wind, and these are done with CSM2, so 22 kilometers. And with CSM2, we were able to carry out longer simulations, so 30-year simulations, and I'm looking at the last 20 years here. And so what you see is kind of what you would expect. The closer you are with your injections towards the polar regions, that's where the temperature starts shifting. But note that for all of the injections, there's some heating in the tropics. And then the cooling in the troposphere follows the regions of where the aerosols are and where you're warming in the stratosphere. And here are the changes in the annual mean zonal mean wind for the last 20 years of these simulations. And you see changes both in the stratosphere and the troposphere. So if we start looking just in this lower stratosphere in the region where the Qbo is located, you see that in some of these simulations, the winds decrease. And some of them, they increase, especially for the equator simulations. So there's a lot of changes, and the changes depend on where you injected the aerosols. And similarly down to the surface, you see a equatorial shift of the stratospheric mid-latitude jet in the 30 north injection, and that's not what you're seeing if you inject in 30 south. Okay, so I'm going to focus in the next 2 slides on the Qbo, because the Qbo also changes the transport of aerosols. So it's not only reactive to what the aerosols are doing, but it depending on which Qbo phase you're in, then the transport in and out of the tropics is also dependent on that. So prior studies without any climate intervention have shown that increased gravity wave momentum flux will lead to a shorter Qbo period. So if you have more waves coming up from the troposphere, then your Qbo period will get shorter. So when you go to a warmer climate and you will get more convection, you expect more generation of convectively generated gravity waves, which will lead to a shorter Qbo period. However, if you increase the residual vertical velocity in the tropical region, then this is going to lead to longer Qbo period because you're going to be preventing the Qbo shear zones from descending down. And I'll mention also that the change in forcing could also manifest in a change in amplitude. So what happens in our CSM2 simulations with the single point injections? A lot of changes to the Qbo. First, let me show you the SSP245 simulations for 2040 to 2070. So you see that the Qbo period is about 20 months. So that is 6 months shorter than the period that we have between 1981 and 2005. I'm not showing you here. So this is just from climate change. And this goes back to the gravity wave parameterization that I put in a long time ago as a postdoc, which links the properties of the gravity waves to the convection below. So as the sea surface temperature is warm, convection is stronger, gravity waves are stronger, then Qbo becomes shorter. And when you add stratospheric aerosols to that, there's subsequent changes to the Qbo. And for example, the largest changes are when you inject at the equator, the Qbo is nearly destroyed. So it goes to perpetual or westerly. And this is something that we have seen in other models. So there have been 2 or 3 studies of the Qbo and SAI. They all focused on tropical injections. And the amount of injection needed to kill the Qbo depends between models, but eventually they all go to this configuration of Qbo being nearly destroyed. On the other hand, when you look at 15 south, we now go to an annual cycle. However, if you look away from the equator for 30 south, 30 north, these Qbos are much more similar to what you're seeing without any climate intervention. I also plotted the Qbo amplitude here. However, I'll note that this is derived from the deseasonalized zonal mean winds, and we're applying all the metrics here that we used in the international QBOI inner comparison. However, those metrics were not really designed for QBOs that change that much. So 15 south injection is showing you a very weak amplitude, and that is because the period is 12 months, and it aliases to the seasonal cycle. So we're basically only looking at the amplitude of the oscillation outside of that 12-month period. So that's why the amplitude is really low. And you can see the reason for why the QBO changes if you look at the vertical velocity, which is on the right. And in particular, I've pointed out the yellow line, the equatorial injection. So you have a very strong change in the W bar star in the tropics, and that prevents basically the shear zones from descending. And then you also, the 15 south, the other location that gives you largest change in the QBO, also has big changes in QBO. So if you want to keep your QBO at present day levels, the best thing to do is to limit your tropical injections, and the smallest impact will be for 30 south and 30 north injections. All right, last slide about the stratosphere, and then we're going to come down to the surface. So I'm looking here at the DJF zonal mean wind. And the reason looking at that is that that's the time when the stratospheric tropospheric coupling is the strongest. So in DJF is often when we get sudden stratospheric warmings, which when the vortex starts reversing, or if there is a strong stratospheric vortex, then it also means that there is actually no impact to the surface. But either way, you want to know what that is. And so in most of these, the stratospheric vortex goes stronger, especially in equatorial injection. However, the changes in the troposphere in the mid-latitudes are very different between the different injection scenarios. So again, contrasting 30 north with 30 south, the 30 north injections move the maximum of the tropospheric jet towards the pole, whereas they move it further towards the equator, they move it further towards the pole for 30 south injections. And that change manifests all the way down to the surface. So these bottom panels show you changes in sea level pressure associated with these changes in mean winds. And the largest changes you see are actually in the Pacific. So you go to a low sea level pressure for injections in 50 north and 30 north, and that's very different for 15 south and 30 south. So we're running a little bit longer simulations of these, or more ensembles, because there's so much variability in the Northern Hemisphere that even with 30 years, we cannot really get down to the mechanisms of this, but it's something that we're working on with Eva at Cornell University. Okay, so finally down to the surface, what do these injections do to the surface temperature and precipitation? So here's annual mean temperature. And two things I'm going to point out, that the injections in the Northern Hemisphere, they primarily cool the Northern Hemisphere, and there is a steep gradient as you go from the tropics to the pole. Whereas if you inject in the Southern Hemisphere, and let's pick this blue line, the 15 south injection, that you see that the changes are pretty equal with latitude, except for a little part here south of -60. And the reason these are not perfectly symmetric is because their continents, our oceans, our sea ice are not symmetric between the Northern and the Southern Hemisphere. Along with the changes in the temperature, there is changes in precipitation. And often we look at precipitation minus evaporation because that's a better measure of water availability. But the changes in precipitation look very similar. So for the Northern Hemispheric injections, so the red and the purple, see that the ITCZ, the intertropical convergence zone, shifts southward, and then it shifts the opposite way for the injections in the opposite hemisphere. And here is a summary of that on the right. All right, so hopefully you've gotten a good idea now that you can use these different locations to try to get you what you want in terms of surface changes. So what we're going to do with these 21st century simulations, both in CSM1 and CSM2, is be smart about it, combining these injections to keep the surface temperature goals, T0, T1, T2 at the target level. And how are we going to do that? Well, this is where we use the methodology developed by our partners at universities, and they've developed a controller algorithm. So before we start WACM on year one, we look at the departure of the global mean temperature from the goal. Based on that, the control estimates the SO2 injections at 15 south, 50 north, 30 south, and 30 north. Then we run the model for a year with the injection rate equally applied throughout the year. Then we stop, and then we do this again. We look how far are we from our goal, we estimate the injections, we put them in, we stop. So we do have the process automated, so we are actually not restarting the model or hand doing that, just the side by side. Okay, so this is GLENS, or the Gene Engineering Large Ensemble. So this is the first large ensemble or medium ensemble of simulations that we applied this controller algorithm in. And as a target, we decided to keep the 2010 to 2030 mean, so roughly 2020 climate. And we started intervention in year 2020. We used the RCP 8.5 scenario, and we ran all the way to the end of the century. Now, I will just mention that we did this mostly to look at high signal to noise at the end of the century. And this is ideally not how SAI would be implemented. You do not want to be continuing injecting aerosols in order to offset more warming. But this was the first study like this, and we really wanted to see how far could we go, and again, just get high signal to noise, because even though we did run 20-member ensemble and these have 20 million core hours, if we only did a much lower amount of injection, it probably would not be able to estimate the surface impacts. So here's again your reference of how much Mount Pinatubo is, and what you see that the controller picked injections primarily at 30 north, 30 south, and a little bit at 15 north. By 2050, we would be injecting the equivalent of about 1 Mount Pinatubo every single year. If you'd gone on like this to 2080, that would be the equivalent of about 2 Mount Pinatubos every single year. So that's a lot of volcanic ash. Okay, how did we do? Well, we actually did really well at keeping our goals. So the black line here is RCP 8.5. Here's Glenn's. Glenn's is staying perfectly on target with global mean temperature. Inner hemispheric temperature gradient is also staying very close to target. And the equator to pole temperature gradient is starting to slip a little bit as we go to the end of the century, but it's still much better than what it is in the RCP 8.5 simulation. So what are the changes at the surface? We're gonna keep this base period as 2010 to 2030, so that was our goal. And we look at the end of the century, 2075 to 2095, and we compare that for temperature and precipitation for RCP 8.5 on the right and for Glenn's on the left. And you see that there are very little residual changes in temperature and in precipitation compared to the climate without any intervention. But there are still side effects. And you expect that because the only way to get back to present day climate is to pull out the emissions of the atmosphere. So climate intervention will never perfectly fix the climate problem, but we can get really close. So the temperature changes are about 2 degrees, and they're mostly in the northern latitudes over Europe, over the Atlantic. And there are some changes in rainfall over India and South Africa. But overall, all the changes in the mean are reduced compared to RCP, and the changes in extremes do go along with that too. What happens in the stratosphere to achieve that at the surface? Well, there are quite a bit of changes. Here's the SO4 mass mixing ratio, and because the injections are mostly at 30 north and 30 south, you see that there is actually a low in the tropical region, which is good because then it allows the QBO to come back to nearly present day, not quite. So here's era interim, RC 8.5. You see that the QBO period goes to 16 months because in our model, it keeps getting shorter and shorter as the Earth warms. But in Glenn's, it actually comes back to something more reasonable. But there is 10 degrees of warming in a tropical stratosphere, which then translates in DJF to a strengthened polar vortex and a weakened jets in tropospheric mid-latitudes, which translates to weaker storm tracks. So everything is connected. So yes, we've changed the climate to perhaps being more livable, but there are substantial differences in the stratosphere in order to achieve that. So Glenn's we ran in 2017, and there are now about 30 papers published looking at various aspects of the Earth system with Glenn's, and those are done by the broader community. I'm going to just highlight here a couple of recent papers. So one by Mari Tai, that's looking on extremes. So mostly the extremes go as the mean, and they are reduced in all the regions, but this Eurasian, Northern Europe, which showed warming in the mean, and you also see changes in warmest nights. But there are a few exceptions. So we also see changes in warmest nights in Glenn's that are not associated with changes in warm temperature. But again, if you look at these changes compared to changes in RCP 8.5, they're much, much smaller. However, total ozone column ozone does not benefit from climate intervention, and the ozone hole recovery is delayed significantly because of all the changes going on in the stratosphere. Here's a recent paper in revision by Christine Shields, who looked at atmospheric river and associated precipitation. And what you do see is still some shifts in the rain. So there is a increase in Southern California in precipitation and a decrease in the Pacific Northwest, especially in the wintertime. So this is still a viable data set for looking at impacts. However, CSM1 WACM is getting a little bit old. So over the last year, I've led the development of another ensemble with CSM2. We're calling this one ARISE SAI, which stands for Assessing Responses and Impacts of Solar Climate Intervention on the Earth System with Stratospheric Aerosol Injection. That's a mouthful, so we'll just stick with ARISE SAI. And 1.5 means that we're cooling to 1.5 degrees C, which in our model is roughly the average temperature between 2020 and 2039. And we try to make the setup in this a little bit more realistic So we're putting in our injections at 22 kilometers, which is more achievable. We're starting intervention in 2035, which is at the point where all the CSM2 WACM ensembles have passed 1.5 C. And we're looking at the more moderate SSP 245 scenario. And we're only running these simulations up to 2070, because we really hope by that time that there will be some stronger mitigation measures in place. And we really don't know. None of this, the SSP 245 and RCP 8.5, they don't have a version in which they start dropping off emissions after a while. So I think maybe we need some additional scenarios, but this is what we had, and we had controls for this. So that's what ARISE is built on. And similarly to Glenn's, you see that ARISE does a great job at keeping at your target temperature. However, here are the residual changes in temperature for ARISE on the left and Glenn's on the right. And the color bar here is a little bit different. That's why you're seeing these changes in Northern Europe a little stronger. But what you also see is that the surface temperature changes that remain in Glenn's and ARISE are nothing alike. So in ARISE, now we have a warming hole in the ocean here, and we have warming over the United States. And along with those changes, there'll come changes in snow cover, which will correlate with the changes in the temperature. So why is this? Why are we getting a completely different answer with CSM2 as compared to CSM1? You can also see this in precipitation. So we were predicting in Glenn's little wetting over Australia. Now we're not, there's no wetting, there's just drying in northern tip. And for India, where it's really dependent on precipitation, we're projecting wetting, and Glenn's was predicting drying. And here is a little zoom in on June through September precipitation, highlighting the monsoon season. That's a figure from a CSU student working on this for his master's thesis. Okay, so what happened? Well, it comes down to where we put in the injections largely. So in Glenn's, recall we did injections in 30 south, 30 north, and we arrived at this distribution of aerosols primarily skewed to the northern hemisphere. And we didn't use the injection at 15 south, hardly at all. However, this is what the algorithm picked in ARISE SAI. So primarily we're injecting at 15 south with little contributions elsewhere. So if you look at the aerosol distribution, it's really heavy in this region between 0 and 30 south, and a little bit more in the extratropical regions. But why? Why would the controller pick this? The answer is that we're setting a different pattern of climate change. So what I'm showing you here is the temperature change between 2050 and 2069 relative to 2020, 2039 for CSM2 WACM just with SSP, so no climate intervention, and CSM1 WACM with RCP 8.5. So firstly, the RCP 8.5 is a stronger scenario, so the changes on the right are going to be bigger, but just focused on the patterns. And what you see is that here, the changes between the tropics and the northern hemisphere are much greater than they are over here. And if you looked in longitude, North America is warmer than Asia. And however, under CSM1, they were warming about the same. So there are very large differences in future climate projections, which could be due to two things. They could be due to different emissions, because now we went to the SSPs, which is what CMIP6 uses, versus the RCPs, what CMIP5 was using. But they could also be due to different model physics and feedback. So which one is the cause? Excuse me. Well, thanks to simulations led by Marika Holland and Cecile Henney, we now know that actually a lot of this has to do with model physics. So if you focus here on the purple line, which is CSM2 low top model with RCP 8.5, and the green line, which is CSM1 with RC 8.5. So the forcings are exactly the same, but the model configuration different. And you look at the surface temperature change, it has a very different pattern. So there's more warming in the northern hemisphere in CSM1 compared to CSM2. So based on that, if you look at the inner hemispheric temperature gradient for the purple line for CSM2, it will be relatively flat, where it is really changing, which is really increasing for CSM1. And also notice that CSM1 Wacom, the blue line, is warming much more quickly than the green line. So these are even models with similar tropospheric physics, but Wacom has different stratospheric physics, which means slightly different polar vortex and different impacts on the surface, perhaps different sea ice feedbacks, etc. So there's quite a bit of uncertainty in model projections. So then if you have the controller decide for you how to offset this, it's going to try to go back to the present climate based on the physics in that model. And it's ending up with very different injections between CSM1 and CSM2. So then if you compare what the DJF winds look like in glens versus Arise, you see that it's no surprise that in the tropics, you see slightly different changes. And then you see different changes in the Northern Hemisphere troposphere. And again, this tropospheric jet is shifted towards the equator in glens, and it's shifted towards the pole in Arise. So when you look at the sea level pressure in these simulations, the patterns are also different. So both have a similar positive NAO type pattern and sea level pressure. However, in Pacific, one has a high and one has a low. So these changes then will translate to changes in storm track, changes in extreme weather, etc. So they're going to be very different impacts. So what we've learned is climate intervention using stratospheric aerosols can reduce the global mean temperature. We can go from a projection like this to a projection like this or like this. And we're not certain which one of these is closer to a reality, but they're both significantly reduce the impacts of climate change as compared to what you see here. And uncertainties come pretty much from every place in the modeling framework. So starting with subgrid scale evolution of aerosols, there's uncertainty how particle size evolves and where they're going, which then translates to the aerosol optical depth. There's uncertainties in stratospheric dynamics, stratospheric chemistry. There's very large uncertainties in clouds and radiation, as most of this includes parametrizations of microphysics, parametrizations of cloud convection, which in terms create uncertainty, modes of variability, which drive teleconnections, etc. So I'm going to zoom in for you on this one of uncertainty in stratospheric dynamics, because as I mentioned from the beginning, the stratospheric dynamics in Wacom are very dependent on gravity wave parametrizations. So in most models that exist right now, there is a gravity wave source that's prescribed at 100 hectopascals. It's constant in time, tuned for present day climate. And even if you're not a climate modeler, just from knowing that these come from fronts and convection is likely to increase in warming climate, you know that this assumption is wrong. It just cannot be true. So that's why in Wacom, we went to this parametrization that depends on the sources. So in the extratropics for non-orographic waves, we launch our waves for frontal systems and from convection. However, these relationships still have uncertainties in them. So the parametrization is based on linear theory and mesoscale simulations, but observations of gravity waves are limited. And it could be that we are overestimating how fast our gravity waves are changing relative to climate. But the main point is that understanding what's in our climate models is crucial to understanding the uncertainties and to communicating those uncertainties to decision makers. And I just gave you an example for one parametrization, but at NCAR, we have expertise in many of them, and every single person you would ask could find you these skeletons in the closet that you know that there is huge uncertainty. So, okay, so lastly, I'm going to talk about partnerships, because partnerships have been crucial to the progress we've made at NCAR with the community. So what we've been doing at NCAR is mainly running the large simulations that are really difficult for community users to do. As I mentioned, GLENS required 20 million core hours. ARISE required 10 million core hours. We put in a lot of new output in ARISE to serve the broader community, and it's just something difficult to do by individual researchers. And we also have the people working on reducing uncertainty. For example, Simona Tilms and ACOM and Mike Mills are working on Karma to get after that uncertainty of any aerosol distribution. We could not be doing our work without our partners at Cornell and Indiana University. They work on scenario strategies and optimization. We are engaged with CSU that are there looking at impacts with Daniel and Lantau. And recently we have Libby Barnes jump on board to look at machine learning to start assessing when would machine learning tell us that the climate is different? Or can we, is the climate with climate intervention exactly the same as present day climate and will not be able to tell? Rutgers University is looking at impacts on crops. And we have researchers from the Decimals Fund looking at impacts in developing countries. They are looking at the things that they care about, and we did our best to try to give them their output. But they're a very important part of the process, as we living here in Boulder, Colorado, really have no idea what people care about in other regions of the world. Then there's Jim Haywood from the Met Office and his team. They are right now running ARISE with the UK ESM model, which will be great for comparison. I didn't mention marine cloud lightning too much, but Jack Chen is working on that at NCAR, and we started a collaboration with University of Washington on that. We're partnering with Silver Lining, who helps us with funding and partnership building. And one particular partnership they help us establish is with the Amazon Web Services, which right now we have about $750,000 in cloud computing. And I'll mention what we're going to do with that. So this is a figure from Dagmar Martin's paper that's just been submitted, talking about what scenarios and strategies we should be running. So we've ran ARISE SAI 1.5 at NCAR. With the allocation from AWS, we're going to run ARISE SAI cooling to 1 degree pre-industrial, 0.5 degree pre-industrial, and also doing a delayed start, so starting intervention in 2045. And Cornell Group has already done some simulations too, so we have an expectation of what to expect. They are running with the middle atmosphere version of the model, which is half the cost. They just run few Ensemble members, and once that's showing good results, then we're going to do the full simulations with the TSMLT chemistry on AWS. So here's a figure by Walker Lee from Cornell University, and looking at sea ice, and basically what it's showing, if you go from different targets, 1.5 C to 0.5 C, you can perfectly, well, not perfectly, but you can recover sea ice to what it was in 2020 levels or even above, which you could not do if we only kept cooling to 1.5 C above pre-industrial. On the right, I'm showing a figure by Brendan Clark from Rutgers University, which shows that actually climate intervention has benefit to crop production over the climate change. So everywhere where you see blue, that's an increase in production, either of maize, rice, spring wheat, or soybean. And you are seeing a lot of orange and red in climate change. So it's great that we have these links to the community, because we're just not able to do all of the analysis in-house. All right, so lastly, I'm going to end with a little bit of future work. And I don't think that climate intervention would be actually implemented how we simulated in ARISE. And the reason is, this suggests that we're just going to go full force and go for many, many years. But I think we would want to have some verification in place that our models are actually capable of simulating all the process correctly, so then the impacts downstream are estimated correctly. So I think how this more likely would go is with small magnitude and duration SO2 injections, more like an individual volcano, maybe 2. And we would need to, given the timeline of when we're going to hit 1.5 C or 2 degrees, we cannot really wait 10 years for an answer. So we need to do this in a more responsive framework before proceeding further. And again, the impacts are for 8 billion people. You would want to make sure that your model is doing the right thing before even considering further implementation. So what you really need is an Earth system prediction framework for climate intervention. Meaning you should need to be able to look at impacts on shorter timescale. So right now we're looking at climate change, climate intervention. It's all on this longer decadal timescale. But we need to be looking shorter. We need to be looking at subseasonal to seasonal, seasonal to interannual, up to 1 month to 2 years, and seasonal to decadal timescale. But I think the subseasonal to interannual timescale is really where it would become crucial to understand if how volcanoes react, and if there were any trial simulations that they would begin in this time scale. Well, luckily, we have over the last 2 years built an Earth system prediction with CSM2. So this is largely what I spend my time doing with Sasha and Jim Edwards, and we have a real-time subseasonal prediction system with CSM2 Wacom. And Steve Yager and others have been for years pioneering seasonal to decadal prediction. So I think their earliest work on this was by Jerry Meal in 2013. So this is really, we've had a lot of experience working on decadal prediction. And that's mostly been with the low top model. So we can easily do the work, and our models are excellent. So their subseasonal prediction skill is equal right now to the NOAA GFS model, the Environment Canada model, the SREL model. And we do need to do a little bit more work on the system to get the chemistry initialization right for subseasonal timescale. And for longer timescales, it's just a matter of computer time or taking the aerosol distribution and feeding it back to the low top model. So I think for the future, we're already doing right now climate simulations and ESP simulations, and we could just easily add climate intervention to this suite of the research. And I think the benefit of that is you get the expertise of all the people who are already working on modes of variability, relationship to extremes, polar climate, ocean, and land. And I just add the aspect of climate intervention. So I hope throughout this presentation, you've seen that the entire Earth system is affected. So having two individuals that are focused on one particular part is not necessarily the best way to move forward. You really need broad expertise, perhaps with small amount of time. And ACOM is already looking at atmospheric chemistry, especially ozone in these climate simulations. They already want to be doing air quality. Well, they're doing air quality prediction with ACOM. It's not integrated with our forecasts yet, but it just needs a little bit optimization, and we could get there. And again, they could help with the chemistry aspect of the climate intervention. The upper atmosphere we need to think about, and we do already have a collaboration with HAO. Nick Petatella did a first complete study of the upper atmosphere response to sudden stratospheric warmings. And lastly, I'll mention that we are putting out a ton of output from these simulations, and we're putting out a lot of output on society relevant information, food, water availability, but we just don't have enough staff to look at it. So there's where I put down unutilized potential, because I think we have researchers in RAL and Cube and just other parts of NCAR that if with a little bit of investment, we could get a lot more people in the organization to get around the problem. All right, so in short, significant progress has been made in climate intervention research in the last decade, and partnerships have been a key to the success. NCAR has played a leading role in providing the broader community state-of-the-art simulations of possible climate intervention strategies. However, large uncertainties exist, and those need to be worked on. And I think we already have all the tools in hand to lead climate intervention studies in the Earth system prediction framework to start providing society that information on shorter timescales. And that's really where the society, looking 30 years out, is really difficult for people, but these short timescales are much more manageable. And lastly, I think we need many bright people to work on this. And for the simple reason that if we ever consider the technology, there's about 8 billion lives that depend on it. So in CGD right now, although you saw a lot of names, that works out to about 2 FTEs. And I think about 1 FTE we have in ACOM. And again, if you think to the scale of the problem, 8 billion people depending on it, perhaps it is just not sufficient. So thank you. And I'll be able to take any questions.
Excellent. Thanks very much, Yaga. We have some time for questions now, so please feel free to raise your hand, or you can enter questions in the chat and I can read them out loud as well. Rich, go ahead.
Yeah, the number that always comes into my mind for this kind of talk, Yaga might know what I'm going to say here, but like you need a 747 to fly into the stratosphere every 10 minutes or something. And I'm wondering, what are there people trying to understand the feasibility of this in terms of where is all that sulfur aerosol going to come from? And do we know the optics and chemistry well enough to make predictions of how the model will respond, even before you think about all the impacts you talked about?
Yeah, so two questions. Yes, there's a person, Wake Smith. He's got an internship with the Harvard Geoengineering, Solar Geoengineering program, and he's worked for Boeing for many, many years. So he is working on that every day. He's got a plan. So yes, there is actually people thinking about where to get the SO2, how to get it up, and how to get it optimally. And also the Harvard Geoengineering program has been trying for years now to get a small, very tiny field experiment going to put the tiniest amount in the stratosphere so we would know how you inject, what happens to those aerosols, how they plume dissolves. Now, they've not been able to succeed with this because there've been opposition. But yeah, the fundament, you can't do this in a lab. So eventually, in order to implement it, somebody's going to have to go and try it. But there's been not a lot of support for that. Yeah, it's a difficult one. But yeah, every step of the way, before you even get to large scale impacts, they did as much as they can in the lab, but there are limits to that.
Thanks.
Okay, we have a question in the chat from Christopher Cruz, who asks, are you beginning to think about actually advocating for such intervention? It seems your results suggest intervention will be less impactful to society than without intervention.
So we just do the research and give people options. So I don't advocate one way or the other. I advocate for actually certainty and for understanding. So I think the worst part, would be not doing the research and getting to 2035 and then doing something really quickly because there is an emergency. And that's actually how people tend to respond. People tend to wait till the water heater breaks and then change it. They wait till the tires are completely blank before changing them. There's part of the human nature, but I think we can't do that for this problem. I think we need to have at least 2 decades of research before we would consider implementing it. So I guess I would say I'm an advocate for early research to see if it's a viable option. And if we would consider it, you really have to do with your eyes open. And the amount of people we have working on it is not enough to get to the point by the time we get 1.5C or 2C. So yeah, I think that if we had to do it with limited research, we would probably be injecting at the equator. And I showed you just in this last 7 years, we've learned this is not where you want to be injecting. So this fundamental research, I think, is very much needed. So the more we understand, the better decision we can make.
Thank you. Next question from Margot Klein, who asks, when SAI experiments are ongoing, what is the response to the dynamics if a large natural eruption goes off?
So largely that would be additive, and you could pause if there was SAI going on. So again, this is where we need models. You would just add that perturbation to the models, and for a while, you would have more, right? So you would have an increase in SAI if a volcano went off, but typically volcanoes are much smaller than the scope of SAI. So like this Tonga eruption that happened, it's a very small fraction of Mount Pinatubo. Actually, Simona and ACOM is starting to model that, but chances are, unless it was a very large volcanic eruption, it would just be a blip.
Great. And in the last 50 seconds, there's a question from Yangyang Zhu, who asks, can you comment a bit more on the different warming responses in the Northern Hemisphere in the different configurations?
So 2 things I'll say, that John Fasulo is really looking closely at these runs, and he's finding a lot of cloud feedbacks. But other than that, I think, in the future, we really need to start paying more attention to what's going on in those northern latitudes and the feedbacks with the sea ice. Those are because that's where the differences have been in between CSM1 and CSM1 WACM.
Excellent. Well, thanks again, Yaga, and thanks everyone for the questions. And I look forward to seeing you all next week.
Thank you all.